Now, in this lecture, we'll find out the radius of the small circle. In the drawing, we have a quarter circle. AOB is a quarter circle. We also know that the radius of this quarter circle AO and OB is equal to 16 units in its length. In addition, inside this quarter circle AOB, we have a semicircle. This is a semicircle, and we have also this small circle with radius capital R, and our mission is to find out the radius of this small circle, that is to say the value of capital R. So first of all, we will define the relevant points of this drawing with letters. We define the center of this semicircle. This point is point P. Likewise, we define the center of this small circle. This point is point Q. We define the point of tendency of tangent OB with this small circle. This point is point M. And here we can implement rule 1. We have the radius OM, the radius QM of this small circle. It is drawn to point M, that is the point of tendency of tangent OB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MO. If tangent OB is perpendicular to the radius MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. I'll repeat quickly on rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So in the drawing you have this circle, and the radius of this circle is R. We have tangent AB, and the point of tendency of tangent AB with this circle is here at point M. And we have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to point of tendency, then tangent AB will be perpendicular to the radius MO. That is to say, if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay, and implemented here, rule 1. According to rule 1, because of the fact that the radius OM is drawn to point M, that is the point of tendency of tangent OB with this small circle, then this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay, and AOB is a quarter circle, and therefore angle AOB must be equal to 90 degrees in its size. So as I mentioned before, AO and OB, they are both the radii of this quarter circle that actually equals to 16 units in its length. So AO equals to 16 and OB also equals to 16. Actually, the diameter of this semicircle is the radius of the quarter circle. I repeat again, the diameter of this semicircle, it is actually the radius of this quarter circle. So the diameter of the semicircle equals to 16 units in its length, and therefore the radius of the semicircle must be equal to half of it. That is to say, it must be equal to 16 over 2, that is 16 over 2, that is 8. So The radius AP of the semicircle is equal to 8 units in its length. Likewise, the radius OP is also of the semicircle is also equal to 8 units in its length. Okay, in the next step we will do a construction. That is to say, from the center of this small circle, that is to say from point Q, we will draw perpendicular on side AO. Repeat again, from point Q, we will draw perpendicular on side AO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and AO. This point is point H. By doing this construction, we can get here quadrilateral QHOM. This is quadrilateral QHOM. Inside this quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral AGQMO, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral AQMO as a rectangle because it has 4 right angles. So I write it down. Quadrilateral OHQM is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side QM must be equal to the opposite side HO. But QM, it is the radius of the small circle that is equal to capital R. Therefore, HO must be equal to capital R. Okay. And in the next step, we join the center of the semicircle, that is point P, with the center of this small circle, that is point Q. But before that, we define the touching point of this small circle with the semicircle. This point is point S. I repeat again, point S is the touching point of the small circle with the semicircle, of the point of tendency of this small circle with the semicircle. And here we can implement rule 10. I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, if those two circles touch each other externally at point P, if those two circles touch each other externally at point P. Point P is the point of tendency of the small circle with this big circle. Then the straight line that connects their centers together. Point M is the center of the small circle, point O is the center of the big circle, MO is the straight line that connects the centers together. So this straight line must pass through their touching point, that is point P. or MPO is one straight line. Okay, MPO is one straight line. Why? Because the straight line MO must pass from point P, therefore MPO is one straight line. You can definitely implement rule 10 in our drawing. Why? Because in our drawing, if we join the center of this small circle that is at point Q with the center of this semicircle that is here at point P, then the straight line QP must pass for the touching point that is point S. Or QSP is one straight line according to rule 9. Again, QSP is one straight line. But what is the definition of line segment PS? Line segment PS starts from point P, that is the center of the semicircle, and ends in point S, that is the point of the semicircle itself. This is exactly the definition of a radius. Therefore, PS is the radius of this semicircle, that equals to 8 units. And what is the definition of line segment SQ? Line segment SQ starts from point Q, that is the center of this small circle, and ends at point S, that is the point on the small circle itself. This is exactly the definition of a radius. Therefore, QS is the radius of this small circle, that is equals to capital R. So in total, the length of the distance between the centers of those two semicircle and the small circle, the distance PQ equals to 8 plus R. So I write it here, PQ, that is the distance between the center of this semicircle and the center of this small circle, is equals to 8 plus R. So here we have what is the length of HP or PH. From the drawing, it is very easy to see that PH equals to PO minus HO. Repeat again, PH equals to PO minus HO. So PH equals to PO is 8, it is the radius of the semicircle that is equals to 8 units in its length, minus HO. HO equals to R, that is the radius of the small circle, that is the radius that we are looking for. So in total we shall find out that PH, this small line segment PH, equals to 8 minus R. Okay. So in the next step, I will copy the green right triangle. I copy the green right triangle PHO in a new page, and we will implement the Pythagoras theorem on this green right triangle P. It is actually triangle PHQ. So we will implement the Pythagoras theorem on this right green triangle PHQ. Okay. We just right now found out that side PH equals to 8 minus R. And this is a right angle according to our construction. Angle PHQ equals to 90 degrees according to our construction. side HQ is unknown. The hypotenuse PQ, we already found out that the hypotenuse PQ equals to 8 plus R in its length. Here by PT is the progression for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Actually, this is the right triangle PHQ that I call it from the original drawing. Side PH equals to 8 minus R, HQ is unknown. The hypotenuse PQ equals to 8 plus R. According to the Pythagoras theorem, in this right triangle PHQ, the square of the hypotenuse, that is PQ square, is equals to PH square plus HQ square. Okay. PQ, the hypotenuse PQ is 8 plus R, therefore PQ square is 8 plus R square, and it must be equal to PH square. PH is 8 minus R, therefore PH square is 8 minus R square plus HQ square. HQ square is the missing side, so we leave it as it is. Here we'll open the brackets on both sides of this equation, equation 1, and we get that on this side of equation 1 we have 8 times R, 8 plus R square. So 8 plus R square equals to 8 square, that is 64, plus R square, plus 2 times 8 times R is plus 16R. And it equals to, on the other side of this equation 1, we have 8 minus R. 8 minus R is 8 minus R square. 8 minus R square equals to 8 square, that is 64, plus R square, minus 2 times 8 times R is minus 16R, plus HQ square. HQ is the missing side, so we leave it as it is. So here we have 64 on both sides of the equation, so 64 will get cancelled. And we have also R square on both sides of this equation 1, so R square also will get cancelled. After we cancelled those two expressions, we left in this side of equation 1 only with 16R. So 16R equals to another side of equation 1, we have minus 16R plus HQ square. So here we get 16R to this equation, equation 1. And we get that according to this equation, equation 1, (16R plus 16R is 32R). So 32R equals to HQ square. (32) equals to 2 times 16. So 2 times 16R equals to HQ square. Here we take a root out of this equation, equation 1. And finally, we get that according to this equation, equation 1, HQ equals to the square root of the square root of 2 times R, and the square root of 16 is 4. And again, according to equation 1, we actually found out that HQ, the length of line segment HQ, is 4 times square root of 2 times R. So I write it down. We actually found out that the length of this side AGQ is equals to 4 times square root of 2r. But we have already found out that AGQMO is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. So in rectangle AGQOM, repeat again, in this rectangle AGQOM, side HQ must be equal to the opposite side OM, but HQ equals to 4 times square root of 2r, therefore OM must be equals to 4 times square root of 2r. Write down OM equals to 4 times square root of 2r. Here we can implement rule 10 because we have an internal notch between this small circle and the big quarter circle. Actually, they are touching each other internally at this point. This is their touching point. Okay, so we define the touching point of this small circle with the big quarter circle. This point is point T. Repeat again, we can definitely implement here rule 10. Repeat quickly on rule 10. According to rule 10, if two circles touch, actually it is rule 9. According to rule 9, if two circles touch each other internally, in the drawing you can see that this small circle touches the big circle at this point, point P. Point P is the point of tendency of the small circle with the big circle. The center of the big circle is here at point O, the center of this small circle is here at point M. So, according to this rule 9, the straight line that connects their centers together, that is to say, the straight line OM, must pass through their touching point. OMP is one straight line. Again, OMP is one straight line, so whenever you have an internal notch between two circles, that is to say, they are touching each other internally, like in this drawing, the big circle touches the small circle internally at point P, then the straight line that connects their centers together, that is to say, the straight line OM must pass through their touching point, that is point P. OMP is one straight line. And according to rule 9, OMP is one straight line. You can implement rule 9 in our drawing. Why? Because in our drawing, this small circle touches the big quarter circle here at point T. Point T is the touching point of the small circle and the big quarter circle. The center of the small circle is here at point Q, the center of the big quarter circle is here at point O. According to rule 9, the straight line that connects their centers together, that is to say, the straight line OQ must pass through point T. Or OQT is one straight line. OQT is one straight line. Okay. You see here, OQT is one straight line, or points O, Q, and T, they are all located on the same straight line. But what is actually the definition of the straight line OT? Actually, the straight line OT starts from point O, that is the center of the quarter circle, and that's at point T, that is a point on the quarter circle itself. Therefore, OT is the radius of the quarter circle. And you know it is given us the question that the radius of the quarter circle equals to 16 units. Therefore, OT is the radius of this quarter circle that is equal to 16 units in its length. So I write it down. OT equals to 16 units in its length is the radius of the quarter circle. What is the definition of line segment QT? Line segment QT starts from the center of the quarter circle, from the center of the small circle, and that's at point T, that is the point of the small circle itself. This is exactly the definition of radius. Therefore, QT is the radius of this small circle, that is equal to R, or capital R. So, what is the length of this line segment QO? From the drawing it is very easy to see that QO equals to QT equals, this is point O. What is the definition of line segment QO? QO equals to TO minus TQ. Again, TO minus TQ equals to TO. So I'll write it down. The length of this line segment QO, it is equals to OT minus QT. So QO, the length of this line segment QO equals to OT, that is 16. It is the radius of the quarter circle, that is equals to 16 units in its length, minus QT. QT is R, it is the radius of the small circle. So in total, we should find out that QT equals to 16 minus R units in its length. So I write it down here. The line segment, the length of this line segment QO is equals to 16 minus R. So in the next step, I'll copy the blue right triangle QOM in a new page, and we will implement the Pythagoras theorem on this right blue triangle QOM. This angle equals to 90 degrees according to rule 1. The length of two tangents and a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So this angle equals to 90 degrees. Therefore, the blue triangle QOM is the right triangle. So copy the right blue triangle QOM in a new page, and we will implement the Pythagoras theorem on this right blue triangle QOM. Side OM equals to R. It is the radius that we are looking for in this question, the radius of the small circle. It is actually side QM that equals to R, and the hypotenuse QO equals to 16 minus R. That is what we just right now found out. And side OM equals to 4 times square root of 2R. Here by PT is the permission for Pythagoras theorem. Actually, this is the right blue triangle QOM that I copied from the original drawing. So according to the Pythagoras theorem, in this right triangle QOM, QO square, that is the square of the hypotenuse, must be equal to QM square plus MO square. So I write it down. This is the equation 2. So QO square, that is the square of the hypotenuse, must be equal to QM square plus OM square. QO equals to 16 minus R, therefore QO square equals to 16 minus R square, and it is equals to QM square. QM is R, therefore QM square is R square plus OM square. OM is 4 times square root of 2R, therefore OM square equals to 4 times square root of 2R square. So here we'll open the brackets of this side of equation, equation 2, and get that according to this equation 2, 16 minus R square equals to 16 squared, that is 256, plus R square, minus 2 times 16 is minus 32, times R is minus 32R. In the other side of this equation 2, we have R square plus 16 times square root of 2R equals to 4 times square root of 2R equals to 4 squared, that is 16. And here the root will be cancelled by the power, and we left only with 2R. So according to equation 2, we found out that 256 plus R square minus 32R equals to R square plus 16 times 2R is 32R. So here we have R square on both sides of this equation 2. So R square will get cancelled. After we cancelled R square, in this side of equation 2 we left only with 256 minus 32R equals to 32R. Here we let 32R to this equation 2, and we get that so in this side of equation 2 we left with 256, and in the other side of equation 2 we have 32R plus 32R is 64R. So 256 equals to 64R. Here we will divide this equation 2 by 64, and we get that according to this equation 2, the values that we are looking for, R equals to 256 over 64 is 4. So actually found out that the radius of this small circle, capital R, equals to 4. Okay, so in the next step I will summarize the lecture. In this lecture, our mission is to find out the radius of this small circle. It is equals to capital R. We have to find out the value of capital R. In the drawing, we have a quarter circle. AOB is a quarter circle. Inside this quarter circle, we have this semicircle and this small circle. Again, our mission is to find out the radius of this small circle that equals to capital R. The value, we have to find out the value of capital R. So first of all, we know that AOB is a quarter circle, therefore this circle equals to 90 degrees. And the radius of the quarter circle is 16. AO equals to OB, they are both the radii of the circle, that is equal to 16 units in its length according to what is given as the question. But the radius of the quarter circle is also the diameter of this semicircle. So if the diameter of this semicircle equals to 16, it means that the radius is 16 over 2, that is 8. So P is the center of the semicircle, therefore AP is equals to 8. This is the radius of the semicircle, and PO is also the radius of the semicircle, is equal to 8. We defined, repeat again, that we defined the center of this semicircle, this point is P, and the center of this small circle, this point is Q. Here we can implement rule 1, because we have here the radius QM that is drawn to point M, that is the point of tendency of tangent OB with this small circle. And whenever you have radius that is drawn to the point of tendency, then tangent OM will be perpendicular to the radius MO. If OM is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. In the next step, from point Q, that is the center of this small circle, we do perpendicular on AO. Again, from point Q, we do perpendicular on AO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and AO, this point as edge. By this construction, create for the other Q edge OM. Inside this quadrangle Q edge OM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4-piece angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this 4-piece angle must be equal to 90 degrees in its size. So inside the quadrangle HQMO, we have 4 right angles, and according to rule 6, any quadrangle that has 4 right angles must be this rectangle flat as square. So we relate to this quadrangle HQMO as rectangle because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle HQMO, side QM must be equal to the opposite side edge O. But QM equals to R, it is the radius of the small circle, therefore edge O must be also equal to R. Here we implemented rule 10, and because this semicircle touches this small circle at this point, that is actually point S. Point S is the point of tendency of this semicircle with this small circle. That is to say, the semicircle and the small circle have an external notch between them at point S. Therefore, we can implement here rule 10. Repeat again on rule 10. According to rule 10, if two circles touch each other externally, here we have the big circle touches this small circle at this point, point P. Point P is the point of tendency of the big circle with the small circle. Then the straight line that connects their centers together, the straight line of the big circle is at point O, the straight line of this small circle is at point M. And the straight line that connects their centers together is the straight line OM, of course. So the straight line OM must pass through their touching point. That is to say, the straight line OM must pass through their touching point, that is point P. Or OPM is one straight line. Again, OPM is one straight line. Okay, again, we can definitely implement here rule 10, because here we have the center of this small circle is at point Q. The center of this semicircle is at point P, and the straight line that connects the centers together is PQ. According to rule 10, the straight line PQ must pass through point S, or PSQ is one straight line. PSQ is one straight line according to rule 10. Okay. We know that PSQ is one straight line. So what is the definition of line segment PS? Line segment PS starts from the center of the semicircle, that is point P, and at that point S, that is the point on the semicircle itself. This is exactly the definition of a radius. Therefore, PS is the radius of the semicircle, that is equal to 8. What is the definition of line segment QS? Line segment QS starts from point Q, that is the center of this small circle, and at point S, that is the point on the small circle itself. So, therefore, QS is the radius of this small circle, that's equal to R. So, in total, PQ equals to 8 plus R. Why? Because we know that PSQ is one straight line, therefore PQ is one straight line, and it is equal to, in total, to 8 plus R. And again, PQ equals to 8 plus R. And here, so we have the green triangle, the green line triangle PQH. We know that PO is the radius of the semicircle, that is equal to 8. We have only found out that HO equals to R. So what is the length of PH? PH equals to PO minus HO. Again, PH equals to PO minus HO. So PH equals to PO, that is 8. It is the radius of the semicircle, that is 8, minus HO. HO is equals to R. So in total, PH equals to 8 minus R. Okay. And so I copied this right green triangle PHQ in Olympiad, and we implemented the Pythagoras theorem on this right triangle P, the right green triangle PHQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle PHQ that I copied from the original drawing. Just right now found out that the hypotenuse PQ equals to 8 plus R. We know that SQ is one straight line, therefore PQ is one straight line. That is actually the hypotenuse of this right triangle PHQ. So the hypotenuse PQ equals to 8 plus R. We have already found out that PH equals to 8 minus R. HQ is the only missing side. So according to the Pythagoras theorem, in this right triangle PHQ, PQ square equals to PH square plus QH square. PQ is 8 plus R, therefore PQ square is 8 plus R square, and it must be equal to PH square. PH is 8 minus R, therefore PH square is 8 minus R square, plus HQ square. HQ is the missing side, so we leave it as it is. So according to equation 1, 8 plus R square equals to 8 minus R square, plus HQ square. Here we open the brackets on both sides of this equation, equation 1, and we get that according to this equation, equation 1, 8 plus R square equals to 8 square, that is 64, plus R square, plus 2 times R, plus 2 times 8, that is 16, times R, in total it is 16R. So in this side of equation 1, we have 64 plus R square plus 16R equals 2. In the other side of this equation, equation 1, we have 8 minus R square. 8 minus R square equals to 8 square, that is 64, plus R square, minus 2 times 8 is minus 16, times R is minus 16R. Plus HQ square. HQ is the missing side, so we leave it as it is. So here, on both sides of this equation 1, we have 64, so 64 will get cancelled. And we also, on both sides of the equation 1, R square, so R square also gets cancelled. After we cancel those two expressions, we left in this side of equation 1 only with 16R. In the other side of equation 1, we left with minus 16R plus HQ square. So according to equation 1, 16R equals to minus 16R plus HQ square. Here we added 16R to this equation, equation 1. If I found out that according to this equation, equation 1, 16R plus 16R is 32R, so 32R equals to HQ square. Here, we took a root out of this equation, equation 1, but before that we know that 32 is 2 times 16, so according to equation 1, 2 times 16 times R equals to HQ square. Here we took a root out of this equation, equation 1, and found out that HQ equals to the square root of 2 times the square root of 16 times R. The square root of 16 is 4, inside the root we left only with 2R. In conclusion, we found out that the length of line segment HQ is equals to 4 times square root of 2r. And again, the length of this line segment HQ is equals to 4 times square root of 2 times r. But we have already found out that quadrilateral HQMO is rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side HQ equals to the opposite side OM. But HQ equals to 4 times square root of 2r, therefore OM must be also equal to 4 times square root of 2 times r. Okay, so in the next step, I copied the blue right triangle QOM in a new page and implemented the Pythagoras theorem in this blue right triangle QOM. Actually, this is the blue right triangle QOM that I copied from the original drawing, but before that, actually implemented here rule 9. We know that this small circle touches the big quarter circle here. This is their touching point. We define the touching point, this point is point T. So actually, the small circle touches the big quarter circle internally at point T. That is to say, they have an internal notch between them at point T. And whenever you have an internal notch between two circles, you can implement rule 9. According to rule 9, if two circles touch each other internally, the small circle touches the big circle here at this point, point P. Point P is the point of tendency of the small circle with the big circle. And we know that the center of the big circle is here at point O, and the center of this small circle is here at point N. So the straight line that connects their centers together, that is to say the straight line OM, must pass for their touching point, that is point P. Or the straight line OM must pass for point P, or OMP is one straight line. Again, OMP is one straight line. We can definitely implement rule 9 in our drawing. Now because the small circle touches the big quarter circle internally at point T, the center of the small circle is at point Q. The center of the big quarter circle is at point O. So the straight line that connects their centers together is the straight line OQ. According to rule 9, the straight line OQ must pass for point D, that is their touching point. That is to say, OQT is one straight line. OQT is one straight line. So if OQT is one straight line, it means that OT is a straight line. So we know that OT is a straight line. But what is exactly the definition of the straight line OT? The straight line OT starts from point O, that is the center of the quarter circle, and then at point T, that is the point of the quarter circle itself. This is exactly the definition of a radius. Therefore, OT is the radius of the big quarter circle. That is equal to 16 units according to what is given as the question. And again, OT is the radius of the big quarter circle. That is equal to 16 units according to what is given as the question. And know that OQT is one straight line according to rule 9. So what is the definition of line segment QT? Line segment QT starts from point Q, that is the center of this small circle, and that's at point T, that is the point of this on this small circle itself. So this is exactly the definition of a radius. Therefore QT is the radius of this small circle, that is equal to R. And because of the fact that OQT is one straight line, it means that OQ must be equal to OT minus QT. Again, OQ must be equal to OT minus QT. Repeat again, OQ must be equal to OT minus QT. So OQ equals to OT, that is 16, minus QT, that is R. So in total, we found out that OQ, the opposite OQ of the blue triangle, equals to 16 minus R units in its length. And this side OM equals to r, it is the radius of this small circle, the radius that we are looking for. And we already found out that side OM equals to 4 times square root of 2r. So copy this right blue triangle OQM in a new page, and we implemented the Pythagoras theorem on this small right blue triangle, on this small blue triangle OQM. This is the right blue triangle that the commit of the original domain. Here by PT is a version for Pythagoras theorem, so according to the Pythagoras theorem, in this right triangle OQM, OQ square equals to OM square plus MO square. Again, OQ square equals to QM square plus OM square. So OQ is 16 minus R, therefore OQ square is 16 minus R square, and it must be equal to QM square. QM is R, therefore QM square is R square, plus OM square. OM is 4 times square root of 2R, therefore OM square is 4 times square root of 2R square. So here, open the bracket on both sides of this equation 2, both sides of this equation 2. We found out that 16 minus R square equals to 16 squared, that is 256, plus R square, minus 2 times 16 is minus 42, times R. And it equals to R square, and 4 times square root of 2R square equals to 4 squared, that is 16. And here the power cancels the root, and we left only with 2R. So according to equation 2, we actually found out that 256 plus R square plus 32R equals to R square plus 16 times 2R. So according to equation 2, 256 plus R square minus 32R equals to R square, and 16 times 2R is 32R. So here we have R square on both sides of this equation 2. So R square will get cancelled. After we cancelled R square, in this side of equation 2 we left only with 256 plus 32R. In the other side of this equation 2 we left only with 32R. So here we added 32R to this equation 2, and finally found out that according to equation 2, this equation 2, 256 equals to 32R plus 32R is 64R. So 256 equals to 64R. Here we divided this equation 2 by 64, and found out actually that R equals to 256 over 64 is 4. So R equals to 4 units in its length. Repeat again. Found out actually that the radius of this small circle, that is the radius that we are looking for in this question, R equals to 4 units in its length. Okay, thank you very much.